Hey everyone, I hope everyone is doing well today. I appreciate you joining with us for the first part of our oil and gas webinar series that we're doing on updating elevation layers for improved site analysis. We're actually doing a monthly series for the oil and gas community, and we have various topics through the end of the year. So as you can see here, these are the topics that are listed, and we're trying to decide which order you want. So we'll definitely have a poll question that will come up that you can look at these, read through them, and see which ones interest you the most and which ones you may like to see next. Our format for these is we will be having a Google Hangout where each one of these topics will be presented with a panel of experts in the oil and gas community, and we will be discussing these topics. Now, if you are interested in being a panelist for this, please let us know. You can email me at alex.mccracken, M-C-C-R-A-C-K-E-N, at excelisviz, which is EXELISVIS.com, and let me know if you're interested in being part of that panel, and I can send you additional information. So what you see right now is the poll on the different topics that we're looking at. So we have ensuring consistent output quality for derived products, effective ways to monitor pipeline encroachment, and then we also have using vegetation to gain insight into production and ops, and the future of oil and gas with predictive analytics. Now, if there is something that you're additionally interested in, please let us know.
All right, I am going to close that poll, and everybody should be able to see our presentation again, and we'll get started. Okay, so the way, thanks Alex for the intro and for all that information. I have organized this webinar into two different sections, probably about 10-12 minutes each of content. We'll leave plenty of time for questions. The first we'll talk about what elevation layers are, why they're important, and how they might be used in oil and gas operations. And the second part, we'll do a deep dive into an actual demo, looking at one of the ways that we can use elevation information or elevation layers to do an analysis on maybe some site placement as an example. So what are elevation layers and why are they important? Well, there are many different elevation layers that you could use or may have. You'll hear them used interchangeably in the term. So DEM, when I talk about that, I'm talking about a digital elevation model that represents the bare earth surface. There's also a DSM, or a digital surface model, and that includes the above surface features like trees and buildings and anything above the ground. A TIN is a triangulated surface representation where more triangles give a more granular representation of the surface, picking up subtle features, and fewer larger triangles that represent more large-scale features, or missing those subtle features, just looking at a general area. A tin surface, by the way, tends to be extremely large, and thus the ability to reduce the resolution or the number of triangles is something that could be useful in speeding the processing, and you can still generate a pretty accurate surface. A lot of people use tin surfaces to represent the surface. Okay, so why are these important? So what you're looking at here is just a general topographic modeling product. It's a, I believe that this is a shaded relief map that's colorized and draped over an elevation surface, a bare earth elevation surface. Some common examples of using elevation layers in oil and gas communities include site planning and pad placement, where bare earth assessments of a new or existing site can help to determine the best places for pad placement while considering not only the flattest areas of terrain, but also considering surface features and the pad placement proximity to the roads and other infrastructure. And that's one of the examples that we'll be looking at in the deep dive. Drainage planning is also a popular application of using elevation layers, where bare earth stems and contours derived from surface information are critical for the creation of drainage plans, which are used to predict the course of seasonal drainage and runoff, things like that. And also drainage maps are useful for spill prevention or mitigation plans as a source of information for potential directional and even velocity analysis where a spill might propagate. One of the biggest differences between the status quo of using ground surveys to gather this information today and remote sensing techniques is that ground surveys on a pad site, for example, might establish a coarse idea of localized depressions where water might pool, whereas remote sensing techniques can produce a much higher resolution surface to identify these localized depressions because the sample rate is much higher. We'll talk a little bit about that. So some people find remote sensing ways to derive surfaces are actually a little bit more useful than ground surveys in some cases. Volumetric analysis is also something significant that we see our customers do. So surface rendering can be used to compute volumes and even to monitor surface changes over time to indicate where maybe a wellhead backflow pit might undergo a change or monitor smaller, large-scale land subsidence that needs to be addressed for safety operations. There's a lot of different reasons to use DEMs and surface information. They're important in a lot of analyses across the board, from operations and planning to mitigation and safety. So now that we know that they're important, there are several different options and places where you can get or produce elevation products. One of those ways is through imagery. So image derived only to resolution of, imagery using stereo pairs. And images that use processes that use images, to derive a surface from stereo pairs. One of the things that you have to remember when using imagery, when you're deriving a stereo generated surface, is that you are generating the DSM, or the surface model, that includes the elevation of the features on top of the surface, and you're also doing so only to the spatial resolution of the imagery itself. So if you're working with 30-meter pixels in your imagery, you're going to end up with a 30-meter DEM at best. A lot of the information out there is very pervasive to use imagery for DEM generation, like Landsat or other satellite imagery. And these can be really good for some analyses that we'll talk about. LiDAR. So if LiDAR is available, you're getting, I have in quotes there, real point clouds, as opposed to image-derived, where the imagery, not only is it constrained to the spatial resolution and the surface features, but you also get a very regular grid with 1 point per pixel. And with LiDAR, you're getting a very irregular grid. Also, the density of the LiDAR point cloud can be variable, and you can get, in many cases, in most cases actually, a much higher resolution surface derived from LiDAR. Some of the excellent sources for height information are DEM, DSM, and TIN. You do need to remember that some people will say the surface features from the LiDAR that you're extracting based on the point density can be very easy to derive with different software packages, including NV. And that's something that can be really useful, especially when you're doing proximity analysis or something like that. SAR is a great source for extracting elevation information. It's more difficult to process at times, although there are intuitive tools out there like SARscape and some other tools. Interferometric SAR processing enables DEM extraction and also land displacement mapping, which are both great for mapping or land subsidence and those types of features. So if you have a data set appropriate for SAR interferometry, it probably also has a temporal component. And SAR processing can leverage this within the same processing workflow as opposed to using time series analysis from imagery or LiDAR. So that's one of the pros of using SAR. And we'll talk a little bit about that. And we'll get into these in a little bit more detail as we look through them. And then lastly, we can't gloss over the fact that there's a lot of existing information out there. There are DEMs that are available already, or surface models available already from various projects. A lot of them are just available free to the public. So we'll start with that, actually, going into a little bit more detail. These are just some sources of elevation layers that already exist. The spatial resolution and the areas of coverage are going to be variable, but there are ways where you may already have access to an elevation layer for your study area, so they're worth a look if you're looking to just download something. The image that we're looking at is from this first link, the United States Interagency Elevation Inventory, which is a new site that was just put up that actually encompassed the other three and some others of a nice concentration of elevation information. And it will say, even for your study area that you zoom in on this map, if it's publicly available or not, and in some cases, if not, a source to go to get to that information if that's what you need. So there are ways out there to just get existing information. If you decide to generate the information yourself, we'll talk about those 3 other processes here. So image-derived elevation layers are generated using algorithms that generate tie points and calculate the relationship between the stereo pairs to derive a surface elevation DSM. So it's a surface model including the things above the Earth. This stereo pair input can be from aerial photos or satellite sensors, and some of the supported sensors are listed here for the MV processing for this. The inputs must have RPC positioning information, and that's rational polynomial coefficients, which is used in the algorithm and the relationship calculations. So note that you can always build the RPCs from the imagery if you have the correct information, or if it's a supported sensor for a rigorous orthorectification model, you can almost use that as opposed if you need to get to that RPCs. The output surfaces, like I said, are DSM surfaces. Scenes with significant surface layers like buildings, trees, or other things do not lend well for the DEM extraction if they're mixed. So some people, for example, if they have a big city on a very steep hill right next to an ocean or something that's really flat, there are ways to mask things out and process things differently to still get a good result. It's just something to be aware of. And then a lot of times, if people use an image-derived surface, they can do things later down the road because what you end up with is just a lat long and a height. And you can do things like feature subtraction to get things off the surface to try and simulate bare Earth if you don't have real LiDAR. So assuming that you do have RPC layers for image-derived stereo DEM extraction, something like the DEM extraction module, which is a workflow that sends you through a stepwise process to extract the DEM from the imagery, is definitely something that would be appropriate to use. What you see here is an anaglyph image, which is displayed as a combination of the right and left epipolar images that are generated from the DEM extraction process. So what the heck did I just say? So let me just describe that. Epipolar geometry is also sometimes called stereogeometry. And that describes the relationship between the image capture planes and the objects that are found in each image. And without getting too mathematically complex here, just go to say that it creates a rotation and a translation from one image to the other along these epipolar planes that takes out the x dimensionality, or I'm sorry, the y dimensionality of the data. So what you end up with are epipolar images where the right and left input pair that are oriented in such a way that each of the ground feature points have the same y coordinate in both images. So you end up with this sort of overlap effect that you're seeing here. What that's called when it's displayed as an RGB combination is an anaglyph. And this anaglyph image, if you have the 3D glasses or the anaglyph glasses, one side's red and one side's blue, this does display in 3 dimensions, and a lot of people really like to use that in this environment when they're doing some tie point refinement, which is something that you can do before extracting the DEM, is examine the tie points in 3 dimensions to adjust the surfaces to get them just the way that you want them before extracting the actual DEM. So that's why I put that up here. And here's the actual DEM that was generated. So that was an aster scene. And the DEM input was the 15-meter pan bands. So that's the best resolution that we can get from the aster data is if we do some pan sharpening using those pan bands and extract the DEM from those. So this would be really suitable for a lot of applications that don't require very high accuracy DEM resolution. And the other thing to note is when performing this type of DEM extraction, it can take a lot of time. There are mechanisms to decrease the resolution, not of the DEM that you're extracting, but it can be downsampled so that it doesn't make as many triangles in the triangulation process, which saves a lot of time in disk space. If you don't need the high resolution requirement, there are ways to refine the DEM in such a way that you can process it quicker while maintaining some accuracy and saving disk space. Okay, so let's move on to LiDAR data. LiDAR data is an excellent source of surface information, and surfaces that are extracted from LiDAR tend to be very accurate. They are in an irregular, more real grid. The supported formats that LiDAR anyway supports are pretty much all of them out there: LAS, LAS, any ASCII XYZ, NITIF, binary SID, CSV, and even if you have a surface that's generated from a stereo pair like we just saw, that's just going to be an ASCII XYZ with a lat long height, and so that could certainly be imported to something like LiDAR to do feature identification or subtraction if you need to. The point density that is required to get some of these topographic product information is very low for this type of analysis. So where you might need several points per square meter to do things like extract trees or buildings, power lines, things like that, to generate surfaces, you need maybe 1 point per square meter, or I've seen it work actually very well with even fewer than 1 point per square meter to get a very good surface representation of your study area. The outputs are very flexible, going to raster or vector formats for raster for the elevation products, vector for the actual features that are extracted. There's a lot of flexibility there. And then one click to export these products directly to ENVI or ARC for analysis. And this is important just to mention because the deep dive analysis that I'll be doing does use vector layers that were generated from a LiDAR point cloud, sent to ArcMap for some buffering, and then back out to ENVI. So that the one-click seamless generation and moving these products around is really useful and kind of important here. And also, your LiDAR point cloud can be processed in batch. So here we're looking at a LiDAR-derived bare earth elevation layer on the left. And on the right, we're looking at the digital surface model, which is representation of the surface features. And this is actually the Boulder Flatirons here in Boulder where we are. And you can see those big Flatiron rock features. And one of the things that you can do once you have the bare earth and the surface information is you can create something that's called a height model. The foresters call it a canopy height model. It's called a lot of different things, but it's the same thing where the surface model and the DEM, you subtract the DEM from the surface model and you're left with elevation features. So you can start to learn about the heights of things or even the changes of the heights over time. So for, say you're doing any sort of pipeline analysis or things like that, and you want to see if there's been any movement, the height model over time would be something that you could use in an easy comparison. So lastly, I'm not going to do a lot here on SAR today or go into too much detail. We actually do have a full new course becoming available soon for SAR processing. That said, just a few notes about SAR data because it is a useful data source for elevation information. High-resolution surface information or deformation characteristics can be extracted from SAR data, including a processing method called interferometry. So some applications of these might include, they're not limited to these, they might include DEM extraction, land displacement mapping to find things like small-scale changes or movements. You can see tire tracks or small shifts in elevation that might be a precursor to an earthquake or some other subsurface event. SAR data and SAR data processing is also useful to track larger scale events like land shift or landslides, earthquake generated or some otherwise. So this image that you're looking here is just a land displacement map that was generated from some differential interferometric SAR processing. And if you want more information on that or go into more detail, please just let me know and I'll get with you offline and we can talk about SAR. Okay, so before we move on to the deep dive, just to kind of break things up, I wanted to put up another poll just to ask about some of the sources that you might use for your elevation layers. And then also, while we're waiting for that poll to come in, I thought that I might just take a question. I'll get to all the questions at the end. But if there are any questions, I'd be happy to take one now while we're answering the poll.
So it looks like we have a few questions coming in here. We'll give it just a second and then we'll pull one out. All right, so we'll use this one. Rebecca, the question is can this process work along a pipeline? So I imagine what they're asking is, you know, doing this aerial survey and elevation-derived products. Since you've been talking about them working on a well site, could it also work along the entirety of a pipeline?
Yeah, great question. Thanks. So I actually just put together a couple of screen caps for a customer who was asking that to me just this week. And what ended up working really well to do some pipeline extraction analysis from elevation information was to look at that height model, so the surface elevation minus the bare earth, and look at that height model to pull out an above-ground pipeline feature using the MV feature extraction with 2 passes to get to the feature, remove the noise, and then actually really extract the pipeline and its elevation along there. So it worked really well with this process. Yes, definitely. And if you have any interest, I'd be happy to send you some screen caps and more information about that. So thanks for the question. Okay, I'm going to close the poll. Okay, now this is where in the webinar that we expect things to kind of go in interesting directions. I'm going to pull up, I'm going to go out of the PowerPoint here and pull up some slides and talk about the processing. So let's see. Okay, so here we have MV LiDAR. I'm just going to move my screens around. So hopefully you can all see, what you should be seeing right now is MV LiDAR with a surface displayed in it. I'm going to assume everybody can see that. Okay, and what we're going to talk about is we've got this LiDAR point cloud, and I need surface information because I want to perform an analysis, and I want to know, I'm going to pull this slide back up just so we can talk about the analysis that we're going to do first. Okay. We want to identify some potentially suitable locations for well pad placement. So I've got a LiDAR point cloud from which I'm going to derive a digital elevation model. I have generated some topographic modeling products, which we'll look at, that I've generated from that DEM, and some proximity information because I've got these criteria to meet where these sites that I might place must not be within 100 meters of existing structures, the buildings. The locations must not be on or within 25 meters of an existing road. And then the topographic modeling analysis that I did, I'm going to use to make sure that I'm putting these sites on flat areas that have a less than 5-degree slope, but they've also got to be big enough to hold my pad. So they must also be at least 1,000 square meters. So we're going to kind of go through some of that and see what those analyses look like. Okay, so now I get this out of the way again. Okay, so here's MV LiDAR, and what we have here is just a terrain that I can kind of move around. I can zoom in and look at the terrain that I processed from my point cloud. If I want to look at the points themselves, I can go in here, zoom in, and do some processing. I did this in advance. LiDAR processing can be fast and very easy, and in fact, in MV LiDAR, it's just a couple button clicks to get to all these products. But it does take time, and so I did that in advance, just to show you here that you can launch products from your point cloud directly into MV or ArcMap. Okay, and I have done that over here. So I'm going to pull up MV. And here is the DEM, or the bare earth surface, that was generated from that point cloud. And I generated it at a 1-meter resolution. One of the things when looking at DEMs, we're used to looking at things in color. You might just want to put a color table on it to get some bearings of what it is that you're looking at. I'll show you some other things here. I'm actually going to choose a different color table. Let's try, oops, okay, that's good enough. Okay, so high areas, low areas. Also from that point cloud, I extracted some buildings. So see those building vectors there? Okay, bear with me. This is the part where live demos kind of, you just got to bear with me. I don't like my color table. I'm going to, I want to get that red out of the low area. Okay, so you can kind of see those layers. Okay, so we've got our buildings. We need the buffer zones around them, and we've also got some roads. So these road layers are here. So these are existing roads, and we can't be around those roads either. And these are our input products. So one of the first things that I did was I decided, okay, I need to have these buffer zones around my my roads and my buildings. So using ArcGIS, just a click of the button, let's create these buffer zones around the roads and around the buildings. And what you can start to see here are some layers, and I'm going to just kind of zoom in here. If I start to change the transparency of these layers, you can kind of see through one to one below, and that's what I've got here going on, is why you can see more than one layer at a time. So for example, here's my road buffer, and here were my roads. So that's 25 meters within a road, and I did the same thing for the buildings. These are the areas that we want to make sure to not put a site. Okay, so those are off limits. The other thing I did is I took my DEM. I'm going to turn these off. I'm just going to turn the DEM back on. I'm going to go back to grayscale, turn off some of these layers, and I need to find the areas that are less than 5-degree slope. So for those of you not familiar with ENVI, what we're looking at here is we're looking at the data here in this display area and all these layers that I've been turning on and off and dragging around over here, interacting with our data here, like that transparency slider. And then on the right here, this toolbox, this is where the meat of the analysis tools in ENVI would live. So hundreds and hundreds of different algorithms and tools, pretty much anything that you need for image analysis. And in this case, it's topographic modeling that I want to do on my DEM, where I want to just look at slope in degrees. I'm just going to export this to memory because I've already done this in advance, but just so that you can see. It's pretty quick to process. Oops. Well, I'm glad that I did that in advance. I'm not sure why that didn't work. But I did that in advance to look at all the areas that have less than 5-degree slope and that are also at least a certain size. And I did that using some clumping and sieving. And I'm going to pull up, just because that kind of blew up there. That's why I do everything in advance. Okay, so this here is the slope map that I constrained to just look at only the pixels that are less than 5-degree slope. So this is the slope map up here, and these are the red is everything less than 5 degrees. And then you see that we have a lot of noise here of these smaller areas that are not suitable based on our size. And I use the sieve tool to just sieve through those and say if it's not at least 1,000 square meters, just delete it, remove it. And also, it's got to be, you know, this might be a suitable area. There's like some tiny little areas in here that, yeah, I'm not really too concerned about. So I can clump these pixels together to a certain degree and still maintain my suitability for my analysis. So that's kind of what I did there. And then what I ended up with is this what you see here. Okay. So now we have our slope less than 5 degrees within a certain area. But our problem here that we have now is if I turn back these buffer zones, especially the roads and my buildings, let's see, I'm going to change the transparency. You can kind of see those. Okay, so what you see here is that some of these areas that fill some criteria are actually sitting in the middle of a road or within areas that I can't put any of my layers. And so what I'm going to do to combine these or kind of fuse this information, it's kind of a data fusion problem now, to say I need things that are, these red areas, but they also have to be not in this green area and not in this road area. And the way I'm going to do that is bandmask. The first thing that I need to do is I need to create some layers where I turn off my roads and I turn off my buildings. Let's see, buildings, those are off. So let's just look at things in full resolution. So what this says is that this raster layer has ones and zeros, where 1 means that that is suitable, it's not on a road, and 0 means that is on a road. Okay, same thing here. Ones and zeros, where 1 is suitable potential, zeros mean no, those are too close to buildings. And then I've also got my layer where I've got my buildings. I'm going to turn this stuff off. With ones and zeros, this time the ones are red is the only difference. Where ones are, yes, these are suitable sites, and zeros mean, no, they're not suitable, they're too near something or not filling another criteria. And when you start to combine these, by changing the transparencies, you can see that we have some suitable layers, maybe here, over here, that might be suitable sites that fill all criteria. And to do that as a data fusion project, we're just going to use bandmask to do that. And that's just band 1, which is road buffer layer where those road zones are off, plus the raster where the building zones are off, plus the area where the non-suitable sites are off. When you add those together, anywhere you end up with a 3, where the pixel is turned on in each image, you're going to actually have a positive hit of a suitable site. And I hope that that makes sense. But what we come up with then is a result that looks like this. And if I actually turn off the background, which I did in this image here, so see that's the background, foreground. What I end up with is only the sites left that are outside that criteria that was built. So that's kind of the workflow of the analysis, and I've got some slides to sort of show this again. I know that's a lot at once. But what you end up with is you end up with just the suitable site potential. You can overlay that on something like your DEM, or even overlay it onto a bitmap and export that to a report or project or as PDF or something like that. Okay, so let's go back to the slides and just kind of recap what we did. Okay, so we talked about the topographic analysis. We talked about cleaning things up and making sure that those sites are not on a road by buffering the road, creating masks for both the buildings and the roads, so that we're ending up with just 3 different layers for input. This is the bandmask expression that I use, just band 1 plus band 2 plus band 3. So each of those layers, where I get a hit in each band, I'm going to replace that with the value of 1 where it's actually a hit. Otherwise, it's going to be a miss. And this is that overlay that I had just shown. And the suitability sites as they are displayed here for the analysis and output. So in a nutshell, that is the discussion of not just DEMs and surface models and how they're used, but some sources and different generation methods for these elevation layers, how those might be useful. And then just a deep dive workflow to just show one example of using these DEMs with external layers for a data fusion problem to look at a workflow of a site placement analysis using these layers. Okay, I know that's a lot. I want to open it up for some questions at this time. We'll go through some questions here. Let's see, Alex, I think, I'm assuming you're still on the line. I'm going to have you go through and read the questions because for some reason I don't have them here in front of me.
Yeah, absolutely. We have one question that is about, looks like where the data is stored. They're asking if we can use data stored on a WCS, which is a web coverage service.
Oh, sure. So that's a great question. So Envy does actually have the ability. What I showed is Envy at the desktop. And even if you're working at Envy at the desktop, you have the ability to go to something called a remote connection manager. And that can let you point to WCS or WMS coverage services. So it's all OGC compliant REST-based endpoint services to ingest information as suitable layers. You can also do that through a web interface if that makes more sense for your workflow as well. So definitely, good question.
And another one here is, what resolution of elevational data would you need to map the well pad runoff?
So I'm going to assume runoff meaning maybe water, hopefully not a spill. So it's kind of a loaded question. I've worked with some customers who've done some hydrologic modeling of their operations sites, and they have been able to generate 50-centimeter DEM to get a very, very good drainage plan map, even 1-meter DEM. The thing that you want to make sure that you're doing is getting the bare earth surface and not the surface features. So LiDAR is actually a really good source of information to create those types of drainage plans, and then those become really good input, kind of midstream input for something like, I think that customer was using an ARC hydro tool or some other hydro tool to see actually where the water would flow in the local sinks and all that kind of stuff. So it's actually a really good way to get a good input layer for some of those modeling projects downstream.
Great. Yeah, looks like those are the main questions here.
We'll stay on the line a few more minutes. If people have other questions, please let us know.
Great. Yeah, and if there are any additional questions, feel free to contact us. As you know, I can be reached for additional questions. Rebecca can as well. All of our information is contained on the website, and we'll be happy to work with you further should any questions come up. Stay tuned to your emails, and we will be sending out additional information on the webinars for the rest of the year as they pertain to oil and gas. Appreciate everyone's feedback on the polls. Looks like there was a lot of interest in the output quality and the predictive analytics topics, so we will try to arrange those accordingly. So if there's no other further questions, I appreciate everyone's time today, and we look forward to engaging with you more in the future. Enjoy the rest of your day.
Thanks so much.